Hello, everybody. Thanks for joining us. So this is the start of a 3-webinar series in which we're going to look at, as advertised, the maths behind PEST and PEST++. Now, at this first talk, I'll talk for about an hour and then we'll have time for questions and answers. Put your questions in the Q&A panel. Behind the scenes is Fiona. I'm John Doherty, by the way. Behind the scenes is Fiona, making sure that air traffic control works okay. So, as we've talked about, as I've said, this is going to be about the maths behind PEST and PEST++, but really the maths isn't too complicated. And as far as I'm concerned, the most important thing is the concepts behind the maths rather than the equations. So if you don't understand every equation, no big deal. And whether you're using PEST, PEST++, or calibrating or doing uncertainty analysis by hand, it's the concepts rather than the details that matter. And that's the important thing for me, that at the end of these 3 webinars, you understand a lot more about just what calibration does and doesn't do, and what uncertainty analysis does and doesn't do. This first of the 3 webinars is perhaps a little boring. It's just a refresher where we're going to talk about things which I'm sure everybody listening to me has already heard at one time or another, except for 1 or 2 things. The exciting stuff happens next webinar and the webinar after. But we need to just cover this first webinar so you'll remember things that are probably deeply hidden in your memory. We'll bring them back to the surface. And then after that, it'll be easy to traverse the topics that are covered in webinars 2 and 3. But today, we're going to be talking about I've got a technical problem here. The slides aren't turning. Excuse me a moment. I'm just going to try to fix this up. Bear with me for a moment. Okay, that's better. Okay, so coming up, we've got a little bit about vectors and matrices, a little bit about statistics, and then at the end, I'll speak for just a couple of minutes as why you've had to listen to all this stuff. And that will be the introduction to the magical stuff which follows in webinars 2 and 3. So as I said, you're not going to hear anything in the next hour that most of you probably don't already know. This is just bringing it up to the surface from the dim recesses of your memories. So let's start off with vectors and matrices. Now, you'll all know that a vector is just a bucket full of numbers. Why do we need to carry around bucketfuls of numbers? Well, we're going to be talking about things like parameters and observations and things like that. So we need a mechanism to carry around bunches of numbers and a way to manipulate them. Vectors are the most convenient way to do that. So a vector is normally just a bunch full of numbers all written in a column. They are indexed according to their position in the column. So 1, 2, 3. In this case, we've got a 5-dimensional vector X with 5 elements. A matrix is a 2-dimensional array of numbers. Its indices tell us about the row and the column number of the respective element. Now, normally, vectors are things that we're interested in, measurements, parameters. The matrices are normally the operations that we perform on those vectors. So let's have a look at these operations. The most basic operation is multiplication. So here I'm saying the vector y equals A times the vector x. A is a matrix. Now, normally with vectors, we use a small letter to represent the vector, bold, and we use a large letter to represent the matrix, also bold. So y equals ax. Let's write it explicitly. Here's our vector y, 4 elements in this case, my matrix A and our vector x. Now, certain rules apply. If we're going to multiply a vector by a matrix, we've got to get the rows and columns right. And the number of rows in the final vector is equal to the number of rows in the matrix. So doing matrix vector by matrix multiplication is easy. So focusing on the first element of this vector, y, we go along the row, down the column. So a11 times x1 plus a12 times x2, etc. This yellow equation describes what we do. Focusing on this second element, we go along the second row of the matrix, down the column of the vector, multiplying and adding as we go. That is a series of linear operations to come up with the second element of the vector y. And so it goes. So that's one way of looking at multiplying a vector by a matrix. You can look at it another way too. We can say this matrix A can be divided into vectors. That's a column vector A1, column vector A2, etc. And if we multiply each one of those column vectors by the respective element of the matrix, add it all together, we get the vector y. And that's signified by this yellow equation here. So we can look at multiplying a vector by a matrix in those two different ways. Which way you look at it is a matter of convenience. Okay, now let's get a little bit more complicated and look at what happens when we multiply a matrix by a matrix. Now, normally we do that if we want to take these two matrix operations, in this case B and A, and combine it into one matrix operation. So operating using the matrix C is the same as operating using the matrix B first, then the matrix A. So let's look at matrix multiplication. I'm writing them out in full. There's my matrix C, my matrix A, and my matrix B. Rules apply. We have to match up rows and columns, but assuming we've done that, the rest is easy. So focusing on this element here, C23, that's the element in row 2, column 3 of this C matrix. I go along row 2 of A, down column 3 of B, multiplying and adding as I go, according to this yellow equation, and that'll give me C23. Similarly, for C32, I go along the third row of A, down the second column of B, multiplying and adding as I go, according to the yellow equation, to give me C32. So as I said before, when we multiply a matrix by a vector, when we multiply a matrix by a matrix, it's like doing two matrix operations in succession. So if I've got a problem and I can't move the slides on. Just bear with me a moment. That works now for some reason. Okay, so if I go C equals AB, that's like combining AB into the single matrix operation. So if Y, the vector Y equals A times the matrix X, and vector X equals B times the matrix Z, then Y equals ABZ equals CZ. Once again, C is just the combination of two matrix operations into a single matrix operation. Okay, let's look at some special operations that we can just do on the transpose, on the matrix. So first one is the transpose. So here's a matrix A, and I'm going to take the transpose of the matrix A. Now with the transpose, I just flip the matrix on its side. Transpose is represented by this little t superscript. So all that does is interchange the rows and columns of the matrix to form another matrix, which is simply the flipped first matrix. Obviously, if we take the transpose of a transposed matrix, we recover the first matrix. And this is a handy little relationship. If I take the transpose of the product of two matrices, I write the matrices in the opposite order and take the transpose of each. This will happen in some of the matrix equations that we deal with in this webinar and in subsequent webinars. So a vector, I've distinguished vectors from matrices, but really a vector is just a 1D matrix, and operations that we can perform on matrices we can perform on vectors. So here's a 5-dimensional vector, a vector X with 5 elements, X1 to X5, 5 rows, 1 column. Here's another vector Y, 5 rows, 1 column. I can take the transpose of this vector X and I can write the elements all in a row. I can do matrix operations on vectors. So here is XTY, often called the dot product. X1 times Y1 plus X2 times Y2 down to X5 times Y5. If two vectors multiplied together in this way, if the dot product of two vectors, X and Y, is 0, those vectors are orthogonal. And orthogonal means that there is 0 projection of X onto Y or Y onto X. Orthogonality is going to be a big deal later on in this webinar and a really big deal in the next webinar when we talk about model calibration. So let's now do the dot product between X and X, that is XTX. The square root of XTX, which is the square root of the sum of the elements squared, is the norm or the length or the magnitude of the vector X, denoted by these double bars. A unit vector is a vector whose magnitude is 1. Let's look at some common types of matrices, matrices that we're going to see again and again over the next 3 webinars. The square matrix, well, obviously a square matrix has the same number of rows as columns. An n by n matrix, n rows, n columns. A symmetric matrix, as the name implies, if you interchange the rows and columns, you get the same matrix. That's the same thing as saying that the matrix is equal to its transpose. A diagonal matrix, as the name implies, has 0 off-diagonal elements and diagonal elements which may or may not be non-zero. But only the diagonal elements are allowed to be non-zero. A special diagonal matrix is the identity matrix. That has zeros for the off-diagonal elements, and the diagonal elements are all 1. Now, the identity matrix has some special properties. If we pre-multiply a vector by the identity matrix, we get the same vector. If we pre or post multiply a matrix by the identity matrix, we get the same matrix. So this identity matrix is a very special matrix. We'll come across it all the time in this and subsequent webinars. Matrix inverse. Now this is getting very close to the subjects of our 3 webinars. We're talking about inversion when we're talking about model calibration, and integral to inversion, and integral to uncertainty analysis. Somewhere or other, we're going to be taking the inverse of a matrix. So let's look at what we mean by that. So we denote the inverse of a matrix by this -1 superscript. This is the mathematical definition of the inverse of a matrix in the green equation. So if we pre or post multiply a matrix by its inverse, we get the identity matrix. Now this has some big repercussions, some very useful repercussions. Suppose that the vector y equals a times the vector x and that the matrix A is square. Let's pre-multiply both sides of that yellow equation by the inverse of A to obtain this pink equation. A -1y equals a -1ax. Well, that's the identity matrix, and we've recovered x. So x equals a -1y. So in summary, if y equals ax and we want to get x and a is square, we just use the inverse of a to recover x. Now, certain rules apply. If a matrix is going to have an inverse, it's got to be square. Not every square matrix has an inverse, and if it doesn't, we call that matrix singular. And this is going to be important later on. Just because a matrix is square doesn't mean it has an inverse. And then concepts like non-uniqueness start to come into the equation. We'll talk a lot about that in the next webinar. Here's a handy matrix identity. AB -1 equals B inverse A inverse. And I'm just going to mention a thing called the determinant of a matrix. It's just signified by these bars on either side of the matrix name. All you need to know about the determinant of a matrix, if the determinant is 0, the matrix is singular. If a matrix is non-singular, its determinant is non-zero. You'll see why that matters in a moment. There's a special type of matrix called a positive definite matrix. Now, this is a kind of a magical matrix, but it's very important in statistics for reasons which you'll see shortly. If a matrix A is positive definite, then you can take any vector x, and regardless of x, except if it's 0, xTAX is positive. Now, these are very special properties, but they're needed in statistics. A positive definite matrix is special in a number of ways. Firstly, it's square. Secondly, it's symmetrical. Third, it's invertible. We need all these for reasons which will become apparent shortly. I'm going to mention briefly the concept of rank deficiency of a matrix. Suppose we've got a matrix A here, which has more rows than it does columns. Suppose also that there's this one column here which can be formulated as a linear combination of these other columns. Now, what this means is that this column's kind of redundant because the information contained in this column is already contained in the other columns. So that matrix is kind of depleted in some ways. It's deficient. It's called, in this case, column rank deficient. Now, this has some important consequences which we'll just look at briefly. Here's my matrix A, and for the moment, we're not going to say whether it's column rank deficient or not. Let me multiply that matrix A, let me pre-multiply that matrix A by its transpose. I get a nice square matrix with the same number of rows and columns as the original number of columns of A. It can be shown that as long as A here is not column rank deficient, ATA is one of these matrices that is positive definite. This is huge when it comes to parameter estimation. Let's talk for a little while about orthonormal matrices. Now, these are huge when we talk about things like singular value decomposition, which is fundamental to an understanding of what model calibration can and can't achieve. We'll talk a lot about that in the next webinar. For the moment, just what does it mean if a matrix is orthonormal? Well, consider the matrix V here, which has more rows than columns, and let's consider that it's orthonormal. So let's look at the column vectors, the vectors which comprise the columns of V. I'm going to call them little v1, little v2, etc. vi, vj, vk, etc. Two things apply. If big V is orthonormal, each one of these columns, these column vectors, has a magnitude of 1. Any one of these columns dot product with another column is 0. That is, any vector which is a column of V is normal to all the other columns of V, and that's expressed by the blue equation. Now, these are special properties, and in many branches of mathematics, we try to analyze things using orthonormal matrices or equations or polynomials or whatever. Normality and orthonormality is huge in mathematics because it makes all kinds of analysis easy and understandable. And we'll be doing that in the next webinar. For the moment, we're just looking at the definitions. So let's look at our orthonormal matrix V. Let's pre-multiply it by its transpose. We get a matrix which is smaller. It's got the same number of rows and columns as the number of columns of V, and that's the identity matrix. This is huge. That's because the columns of V each have a magnitude of 1 and each are normal to each other. Now let's do things the opposite way. Let's post-multiply V by VT. You get a bigger matrix, same number of rows and columns as the number of rows of V. This is not the identity matrix in this bigger vector space. This is actually, though, a very special matrix. So here's our matrix V, and it's got a number of columns, each of which are normal to each other. These span a subspace of vector space. This VVT matrix is a projection operator that we can apply to any vector. If we pre-multiply by VVT, we project that vector onto a subspace of vector space which is spanned by the columns of V. And if we pre-multiply that vector x by I minus VVT, then we do an orthogonal projection of x onto the orthogonal complement of the vector subspace, which is spanned by the columns of V. This is very big, very important when we talk about model calibration next webinar. If our orthonormal matrix is square, therefore, we don't have subspaces of vector space anymore. These columns span all of the vector space. In which case, if we pre-multiply or post-multiply V by its transpose, we have the identity matrix, which says that the transpose of an orthonormal matrix is its inverse. This is big because the things we can do with that little relationship are enormous. And remember, when we're talking about calibration, when we're talking about uncertainty analysis, inverses are everywhere. And constituting these relationships in terms of orthonormal matrices means taking an inverse is trivial, and we can do powerful and very insightful things, which is what we'll do next webinar. Before we finish talking about matrices, I'm going to show you an amazing matrix identity. Now, this may not look too amazing to you, but this is actually huge. That this manipulation of matrices on the left gives us the same answer as what's on the right. We're going to see equations of this type involving 3 different matrices in these order on many occasions on webinars 2 and 3. And we're going to use this identity a lot. Let me just preempt those discussions to show you an important outcome of this identity. And let's focus on the inverse that we've got to take. No matter what we do, whether we're doing uncertainty analysis or calibration, we're going to be taking inverses somewhere or another. And taking an inverse numerically inside a computer is hard work. The smaller the matrix, the easier it is to take that inverse. So let's focus on this matrix B. Now, preempting discussions which are coming up, this matrix B is a Jacobian matrix. This is at the heart of so many things that we're going to do in the next couple of webinars. Suppose B has more rows than columns. When I take this inverse here, I'm taking the inverse of a relatively small matrix by the time I do these matrix multiplications. If, however, I use the right-hand expression to come up with the same matrix, I've got to take the inverse of a much larger matrix. So if B is longer, deeper than it is wide, that's the equation I want to use. On the other hand, if B is wider than it is deep, the matrix is smaller that I have to invert. If I use this formulation, that's the one I want to use. And we'll leave it at that for now. And we'll move on to statistics. Now, all I've showed you, that's all the matrix operations you need to know to do all the magic we're going to do in the next couple of webinars. Similarly, there's not too much about statistics that you have to know. This brief refresher will bring stuff back up to the surface, and then you've got all you need to know to do the next 2 webinars magic. We can't talk about statistics without talking about probability density functions. So I've just generated some random numbers here, and I've just separated them a little bit vertically so you can see them. Now, I want to characterize with random numbers. Now, it means I don't know the value of a random variable, but I know something about it. And we use the concept of the probability density function to tell us what we can know about that random number. We can't know its value, but we can know something about its propensity to take on some values in preference to others. So let me move across here and count the dots in these little yellow rectangles. And I can draw a curve of the number of dots with each one of those rectangles. These random numbers were sampled from a normal distribution. The value of that random variable cannot be less than A, it cannot be greater than B. And I use this function in purple here, the fx, that probability density function of the random variable x, to tell me about the propensity of x to take on any value. And that then tells me all I can know about x. I don't know its value. It can be different each time I do a realization. What I can know, it has got as much chance of being this value as this value as this value, but no chance of being less than A or greater than B. One fundamental rule about a probability density function, it has to integrate to 1. That's saying that the random number has to be something. It can't be nothing. Now, let's look at another type of distribution. So again, I've generated my random numbers and separated them vertically a little bit here so you can see whether they're more and less dense. I'm going to count the number of dots in each one of these rectangles. And I come up with a curve like this. And this is the bell-shaped curve, which you all know about, that characterizes the normal or the Gaussian probability distribution. There's the equation, with which you're all familiar, I'm sure. And like any other probability density function, the area under the normal distribution integrates to 1. Now, we use the normal distribution a lot. Why do we use it a lot? Well, it's mathematically extremely convenient, as it turns out. But convenience isn't just the only reason. Natural processes, if you add them all up together and overlay them on top of each other, there's this theorem called the central limit theorem, which says overlaying natural processes tend to have a normal distribution. So it's a kind of a natural distribution as well. Now, often we don't use a full probability density function to characterize a random variable. We can summarize its randomness just using mean and variance. The square root of variance is standard deviation. So let's see how to do this. This is the definition of the mean. It's the expected value of a random variable. Mathematically, we obtain that by integrating the random variable times its probability density function from negative to positive infinity. If we don't actually know fx, but just have a lot of samples, we can calculate an approximation to the mean simply by summing the values of the variables and dividing by the number of samples that we've got. You all know that. You've done that 1,000 times. So for the uniform distribution, the blue equation tells us the mean. For the normal distribution, there's the mean right at its peak. It's a symmetrical distribution. And the mean is built right into the equation of the probability density function of the normal distribution. Now, another thing we need to characterize a random variable is its propensity to deviate from that mean. The variance of a random variable is the expected value of x of the variable minus its mean squared. That's the mathematical definition of that propensity. If we don't know fx, the probability density function, but have a whole lot of samples of that random variable, we can calculate an approximation to the variance by summing up xi minus the mean of x squared, dividing by the number of samples, or n minus 1 more properly, to obtain an approximation, an empirical approximation to the variance of that random variable. The standard deviation, which is a little more convenient because it doesn't involve the square, is just the square of the variance. So for our uniform distribution, the green equation gives us the standard deviation. For our normal distribution, well, the standard deviation is built right into the equation. Again, this is a propensity to wiggle about the mean, about the central tendency. Okay, that's random numbers. We're dealing with collections of random numbers. We're dealing with random vectors. So here's a random vector with 5 elements. So it's a 5-dimensional random vector X. It's a random vector because each one of its elements is random. Therefore, each one of its elements has a mean and a standard deviation. The mean of the random vector X, which I'm denoting here as X bar, is simply a vector, the elements of which are the means of the respective elements of the vector. That's easy. But now I want to characterize the wiggle room, the variability of the elements of that vector. And this gets a little bit more complicated than just characterizing the variability of a single random variable. So to understand that, let's focus on a 2-dimensional random vector in which x1 and x2 are random variables. And just to make life a little bit easier, let's assume that these have a Gaussian, that is a normal distribution. Suppose that I generate lots of different samples of x1 and x2 and then plot them up one against the other. And I end up with this cloud here. So I can study the randomness of x1 alone simply by counting the dots. I can come up with what's called the marginal probability distribution of x1, which in this case is just a bell-shaped curve with a mean and a standard deviation. This is the probability distribution of x1, the mean and the standard deviation of x1, and I don't care what x2 is. That's called the marginal properties of x1. I can do the same for x2. I can come up with a marginal probability distribution for x2, which is characterized by a mean and a standard deviation. But if I'm going to give a complete stochastic description of that random vector comprised of x1 and x2, I've got to say a little bit more about than just the mean and the standard deviation of each. I've got to say something about the fact that these dots are not aligned along the x1 or the x2 axis. There's some statistical interdependence between x1 and x2, and that's got to be there in the stochastic description of the variability of that random vector x. So let's look at how to do that. Firstly, let's explore what it means by the fact that this cloud is not oriented parallel to x1 or parallel to x2. Suppose I acquire the value of x2. Suddenly, I know something about x1. Now, I don't know its value because x1 is still random, but I know something more about it than what I used to know. And what does knowing something mean? Knowing something means it's got a slimmer probability distribution, a smaller standard deviation. This is called the conditional probability distribution of x1, conditional on knowing x2. So by knowing x2, I now have a conditional probability distribution of x1 characterized by a conditional mean and a conditional standard deviation. The conditional mean varies depending on the value of x2. Because this is a normal distribution, the conditional standard deviation doesn't. But the point here is this conditional probability distribution follows from the fact that x1 and x2 are not statistically independent. Therefore, I can condition x1 by knowing x2. And conditioning means I know something about x2 or x1 by knowing something about x2, by knowing the value of x2. Similarly, by knowing the value of x1, I can obtain a conditional probability distribution of x2. The mean varies depending on x1. Because it's a Gaussian probability distribution, the standard deviation doesn't. Now, in my statistical description of this random vector, x1, x2, I've got to incorporate the fact that conditioning can occur. The fact that knowing something about one tells me about the other. To do that, I use this thing called a covariance matrix. So here's my random vector x, x1, x2, individual random variables. A stochastic description of the variability of these requires a 2x2 matrix, a covariance matrix. This is a symmetric matrix. This element equals this element. Drawing it as a picture, that's the variance of x1, which pertains to the marginal variability of x1. Down here, we have the variance of x2 pertaining to the marginal variability of x2. The off-diagonal elements tell me about the statistical interrelatedness of x1 and x2. That is the propensity for this swarm of dots to be not parallel to the x1 or x2 axis. If this swarm was parallel to x1 or x2 axis, x1 is independent of x2 statistically, and these off-diagonal elements would be 0. So let's generalize this. Here's an n-dimensional random vector x. To characterize the variability of its elements, we need an n by n covariance matrix Cx. The variances are down the diagonal of the individual elements. The off-diagonal elements tell me the covariance between any pair of elements. Sigma 1, 3 tells me the covariance between x1 and x3. More explicitly, down the diagonal, we have the variance of x1, x2, x3. Here's our formula for variance, the expected value of the variable minus its mean squared. If we only have samples, we can compute an empirical value for that variance through this well-known summation, xi minus the mean of x squared divided by the number of samples, or n minus 1. The off-diagonal elements, that's the definition of covariance between two elements. The expected value of xi minus the mean of xi times xj minus the mean of xj. If all I have is the samples, I can get an empirical expression for that, an approximation to that. The sum of xi minus the mean of xi, xj minus the mean of xj divided by n. This will become pretty important when we talk about ensembles in webinar 3. So, some properties of a covariance matrix: it's positive definite. Therefore it's symmetrical, and therefore it's invertible. And this is important because here is the equation for a multi-Gaussian probability distribution. This is the probability density function of the random vector x on the assumption that the elements of X are all normally vary according to a normal distribution. And look, at the center here, we have the inverse of the covariance matrix of X. So that covariance matrix has to be invertible. Here's the determinant of CX. So it has to be invertible. And positive definite. Well, X minus XT, sig negative 1X, X minus X has to be a positive number so that when we put a negative inside of it and then use it in an exponent, that number doesn't go wild. So inside the square brackets has to be negative. Now, the inverse of a positive definite matrix is also positive definite. So the positive definiteness of CX gives us a guarantee that this exponent doesn't blow up. So all these things come together when we use that covariance matrix in part of the definition of the multivariate probability distribution. A little bit more about independent and conditional distributions. Now, this just gets a little bit harder, not much harder, and then it gets easy again. Suppose I've got a random vector Z, which has got two vectors in it, one vector on top of the other. Now, you can think about these as just two numbers or two vectors. The same equations apply that we're going to show. Suppose, and for the sake of a picture, these are just scalars. X and Y are just random variables. If this cloud of dots is oriented parallel to the axis, then X is statistically independent of Y. So the joint probability distribution of Z, which is the joint probability distribution of X on top of Y, or we can write it that way, can be shown to be the product of the individual probability distributions of X and Y. This is the definition of independence. We multiply these two together to get the cumulative probability distribution. However, if we've got this situation, things are a little more complicated. To formulate the cumulative probability distribution of X, Y, that is Z, the formula has to take into account the fact that conditioning can occur because of the statistical interrelatedness between X and Y. So in this case, Fz, that is the cumulative probability distribution of X and Y, is the, or that arrow actually should point here, sorry, is the conditional probability distribution of X conditional on Y times the marginal probability distribution of Y. Therefore, dividing both sides by Fy, the conditional probability distribution of X, that is the probability distribution of X conditional on Y, equals the cumulative probability distribution divided by the marginal probability distribution of Y. This is getting very close to Bayes' equation, which we'll talk a lot about in webinar 3. Note also, looking at this first equation, that if we integrate this equation from negative to infinity, we integrate out Y to come up with the marginal probability density function of X. And we'll leave it nearly at that. So consider the random vector XY, the mean of XY, of that is the mean of Z is just the mean of the individual vectors. Let's denote the covariance matrix of XY this way, where we're partitioning that covariance matrix into the covariance matrix of the vector X, the covariance matrix of the vector Y, and the cross covariances between them. So we've simply partitioned this positive definite matrix into this matrix. Now, here are a couple of magical formulae. If this joint vector x on top of y is multi-Gaussian, then if I know y, I'm going to call it yc, I can very easily calculate the conditional mean of x using this formula. It involves the marginal mean of x, the value of y that I've just acquired, the marginal mean of y, and a couple of these submatrices. And here's another magical formula. If I've just acquired knowledge of yc, because of what we said before, I've acquired knowledge of x expressed as a conditional probability distribution with less variability than its marginal. Here is the covariance matrix that characterizes this conditional probability distribution. It's the marginal covariance matrix times just a combination of these matrices here. So that effective conditioning, this acquisition of knowledge of x through having acquired knowledge of y, can be very easily expressed by these two equations. Suddenly, I have the conditional mean and conditional probability distribution of x. Why does this matter? Well, consider a couple of random vectors we're going to talk a lot about coming up in the next webinars. Parameters of a model and model outputs. Parameters of a model are random variables. I don't know the hydraulic properties under the ground. Therefore, model outputs are random variables, x and y. What if I suddenly acquire, through field measurements, values for those model outputs? I can use these equations to condition the parameters. Therefore, reduce the uncertainties of those parameters. This is what we'll do in webinar 3 using equations based on these same concepts. Okay, it gets easier from here on in, and we're drawing to a close. Here is a simple equation which we're going to use all the time. In fact, there's hardly any equation that I use more often than the equation that I'm going to show you. Suppose we have a random vector x, and we operate on that random vector x using the matrix A to obtain y. Well, if x is random, y is random. Therefore, it's got to have a mean and a covariance matrix. Here's the mean. Simply A times the mean x. Here's the covariance matrix. Using this simple equation, I propagate, as it's called, variance of x to variance of y. We'll use that all the time. Just want to say a few words now about spatial correlation before we finish up. Now I'm getting close now to where I can apply this. So let's talk about a model domain. And let's say this is a map of, say, the spatial variability of hydraulic properties, say hydraulic conductivity. Now, if I'm going to use this in a model, I'm going to draw a grid over it. And if I want to look at the hydraulic property in each element of this grid, I've got this enormous random vector K, which is the hydraulic property in each one of these cells. It's random because I don't know that hydraulic property. I know something about it, therefore it can have a probability distribution. But I don't know everything about it, therefore it has to be expressed stochastically. This K has to have a mean and a covariance matrix. Now just say this is 100 by 100. Therefore, suddenly I've got a problem. I've got to come up with a covariance matrix that's got 10,000 elements, and I need a value for every one of those elements. Well, it's not quite as bad as that. Covariance matrix is symmetrical, so I only need 5,000 numbers. How am I going to get 5,000 numbers to fill the elements of that covariance matrix? Well, if we're prepared to make a few approximations, this is actually pretty easy. Let's just examine what those approximations are. But keeping in mind they are approximations, they're applicable a lot of times, almost applicable a lot more times, and inapplicable other times, just like any approximation. So what is CK? Well, let's start by recognizing that these variables are not statistically independent. If K is higher here, it's probably going to be high here and here too. That is, we expect that if there's anomalous values of K, it's going to pertain to a certain area. You can't have very high in one place and very low in the next cell. Geological media aren't like that. So that implies we've got some kind of spatial correlation here, that there's a statistical independence between K in one cell and K in the next. It also implies that that statistical independence decays with distance. So can we build that into an expression that'll make construction of this CK matrix easier? Well, let's go ahead and do that. We know, however, that CK has off-diagonal elements. There is statistical interrelatedness between the elements of K if they're close together. Okay, so you've got to build this enormous CK matrix. And we often call this the prior covariance matrix because this kind of summarizes our knowledge before we actually go into the calibration process. To do this, and most of you are probably familiar with this, we often use this thing called a semi-variogram. This is basic geostatistics. The semi-variogram, often just called a variogram, characterized by gamma, we say that we're going to characterize the propensity for similarity of hydraulic properties by this gamma function, which is the expected value of Ki minus Kj squared. And that expected value is going to be smaller the closer is Ki to Kj. Now let's make a very big assumption. This assumption is called stationarity. Let's assume that the propensity of Ki to be close to Kj is a function only of the distance between them. And let's further assume that that function is the same here as it is here, as it is here, as it is here. That function does not vary throughout the model domain. This is a huge assumption. Used with caution, but can be very convenient. So that then becomes our variogram. The variogram is a function h of the distance between any two points at which we want the hydraulic property. And the variogram will look like this, gamma as a function of h. If points are close together, the variability, the difference between those points squared is likely to be small. We get out to a certain distance called the range, where the variability between them can be anything, just the innate variability of that hydraulic property. This innate variability is called the sill. So what we've done now is that we've characterized the statistical independence throughout this model domain of the hydraulic properties. We don't need 5,000 numbers anymore. We just need two, the range and the sill. And once we've got the range and the sill, it's an easy matter to calculate the elements of our covariance matrix from this variogram. We may be able to characterize this variogram from field measurements. Generally in groundwater, we don't have enough, we just guess it. But if we can come up with a range and a sill, we can come up with a very easy way to build that covariance matrix, that prior covariance matrix, and all we need is two numbers, the range and the sill, and then we can build our CK. However, couple of points of caution here. We can't just use any equation for the variogram. This covariance matrix has to be positive definite, so only certain equations apply. And the common ones are spherical, Gaussian, exponential, and linear. So that's how we can very rapidly build a CK matrix in our groundwater modeling world to characterize statistically the randomness of model parameters. Okay, finally, let's finish up. Why am I telling you all this? Well, firstly, I've told you all you need to know pretty much for what happens in the next 2 webinars. And in those next 2 webinars, we're going to look at calibration and uncertainty analysis. And we don't need to know much to do an awful lot of powerful stuff. So here's our situation as groundwater modelers. We're going to build a model. And that model's got parameters. It's got a big vector K full of parameters. We're going to use that model to calculate things, heads, fluxes. You're going to make a big approximation. We're going to say that the action of that model on the parameters is characterized by a matrix, Z. That means it's linear. Now that's not right because it's not linear, but that's a good enough approximation for our purposes, and we can overcome the linearity assumption by applying all the equations we talk about in the next 2 webinars iteratively. So this is of enormous help, but it can be accommodated even though it's an approximation. And then we have measurements. We have measurements of the outputs of this model, the Earth model, except those measurements are contaminated by, I'm going to call it measurement error. And I'm going to characterize the measurements by H and the measurement error by epsilon. Now, this measurement error, well, this is a big discussion. It's more than measurement error. I'm going to call measurement error. I'm going to apply that term to whatever it is that stops us being able to fit the outputs of this model perfectly. That is, what I'm saying is that what I observe is the outputs of a notional model, an Earth model, plus some other stuff. Now, that other stuff is going to include measurement error, and it's also going to include inadequacies of the model. But by calling it measurement error, it allows me to give a certain statistical description to epsilon, which makes handling this whole thing a lot easier. So there's the equation of my life as a groundwater modeler. What I observe in the field is the action of the model on parameters plus some random number, which I'm going to assume has the same statistical properties as measurement noise. So Z, I'm going to say it's linear, and therefore that Z is a thing called the Jacobian matrix, just a matrix full of partial derivatives, that is sensitivities. The first column is the derivative of all model outputs for which I've got field data to the first parameter, and the second parameter up to the nth parameter. And what do I know before I start this modeling enterprise? Well, I've got a site. I've built a model. I know something about the hydraulic properties of that site from site characterization. I don't know the exact properties, therefore K is a random variable. But I know something. So I know the expected value because I know the geology. So I know the mean of K. And I know something about the nature of the ability, the propensity for the properties to vary from that mean and the nature of the spatial correlation. So notionally, at least, I have a CK matrix. So before I go into any kind of modeling, I've got a K vector, a mean of K, and a CK that come from site characterization studies, the prior mean, the prior covariance matrix. Then, of course, I have my field measurements. And then I've got this thing epsilon, whatever it is that stops me being able to fit perfectly with model outputs, the field data. I'm going to assume that the mean of epsilon is 0 and that its off-diagonal elements are 0. That is, C epsilon is a diagonal matrix. Now, that's an awfully big assumption, but it's an awfully convenient assumption. and we'll stick with it just for the sake of convenience. There are ways that we can accommodate the fact that it's not a diagonal matrix, but we won't go there over the next couple of webinars. So this is what I know as I go into modeling. K in its statistical properties, measurements, and a reason that I can't fit those measurements perfectly with my model. That reason is a random vector epsilon with a mean of 0 and a diagonal covariance matrix. And next webinar, we will proceed from that point to look first at calibration and then at uncertainty analysis. So that's the end of the first webinar. And if anyone has any questions, now is the time to ask them. And if there's no questions, then now is the time to stop. So you've still got everyone's still here. So either no one has a question because I've explained it so well. Oh, there's a question. There's a question. But I can't see it in the... So Giovanni, you're asking a question.
So I've allowed them to talk, John, so they should be able to ask the question live.
That is excellent. Good.
Can you hear?
I can.
Hear me?
Yes.
Ah, okay, cool. Just the last equation. Don't you reckon that epsilon includes also the conceptual model error?
Of course.
Yeah.
Of course. And if we want to say what is responsible for failure to get a good fit between model outputs and data, it is a heck of a lot more than measurement noise. But then as soon as we start talking about structural noise, and it's not just a conceptual model, it's a numerical model, then that C epsilon has got off-diagonal elements. Okay, what are those off-diagonal elements? This is too horrible to think about. So yes, there are ways to handle this, but we generally assume, and probably it's not a crime against humanity to assume it, that most of our uncertainty is going to come from non-uniqueness, and the lack of ability to get a good fit is certainly going to contribute to the uncertainty of parameters and predictions, but it's probably a secondary effect. Therefore, that's our feeble excuse for ignoring the off-diagonal elements of epsilon. So that's the feeble answer to your question, Giovanni. Any other questions? So could you please explain with an example on how we characterize CX from field info? Well, for the covariance matrix of, so let me just wind, oh, I can't. Just a minute, I was going to wind back these slides, but something is stopping me. Just a minute, page up. Nothing is allowing me. Just a minute. Bear with me a moment. I won't then. Okay, how do we characterize CK? Well, I mean, that's a real good question. And the best answer to that question is a studious and learned guess. Now, we can assume, for example, that stationarity applies. You may have done pump tests all over a model domain, and you may build a variogram and get your CK from that. Well, if you have, well done. In most cases, all we can do is really take a guess. We can say, well, given the geology of this area, I'll say that it's plus or minus an order of magnitude, and let's assume that the spatial correlation is a couple of kilometers. Now that's pretty poor, I'll agree. A complete characterization of the randomness of hydraulic properties in an area is a whole field of study called geostatistics. Now, by taking geostatistics and plonking it into a covariance matrix under the assumption of stationarity, in some ways is a pretty terrible thing to do. However, plan B is pretty terrible too, and anything we do will be approximate. So in a lot of cases, let's take the easy approximation rather than the difficult approximation, but let's have no illusions that it is an approximation And it'll give us, in most cases, a pretty good idea of uncertainty. But in important cases where things like connectedness of conductive features matter, then maybe it's not a very good approximation to uncertainty and we have to do better. But the technology for handling connected conductivity, it's still a little bit vague. We still don't really have the technology to do that well. It's being developed, so it's still a challenge. Okay, for a surface water model, what's the best way to define the prior? Well, like defining the prior, it's always going to be a black art. So, you know, what's the best way to perform a black art? Well, it depends on the nature of the crime against humanity that you want to commit as a modeler. And that's always a personal choice. Now, when you say surface water model, so I'm not sure whether you mean a lump parameter surface water model or something which is more distributed parameters. And in a lot of surface water models like Sacramento model, if that's the kind of thing you're talking about, there's maybe too much lumping going on. And that, as we'll talk about in webinar 3, when you reduce the number of parameters to all that you can estimate and you wipe out non-uniqueness, then you've probably destroyed your ability to quantify uncertainty. And you've, at the same time, you don't need a prior because you can't quantify the ramifications of non-uniqueness. So there's a lot of ifs and buts to that question. But in general, I'd say the same rules apply as in groundwater modeling. You know, an educated guess. Are the parameters likely to be statistically independent of each other? If not, you've got to come up with a covariance matrix. Is that covariance matrix going to be an outcome of spatial covariance? Or is it going to be the fact that, for example, two different types of property, such as hydraulic conductivity and storage coefficient, may be related because they may each be back calculable from, say, porosity? If that's the case, and you've got to come up with a different way of expressing the covariance between those parameters. But that's the subject for another day. But I can say that coming up with a prior is a totally legitimate question, and it's probably something to which we have not paid enough attention to in the environmental industry, and is something that is deserving of a huge amount of attention, especially, as we'll talk about in the next 2 webinars, we can handle and should handle highly parameterized systems. Then we cannot work in a highly parameterized model domain unless we have a good way of characterizing the prior. And that's something which we urgently need better skills. Sorry that the answer to your question is not more satisfactory. Any other questions? Well, okay. How does scale dependence affect calculation of CK? Oh, another excellent question. And again, this is a subject which, in my opinion, has received way too little attention. Any model, any environmental model, any spatial model is going to involve a large degree of upscaling. It's going to involve upscaling of hydraulic properties and upscaling of hydraulic processes. And the question implies that the statistical descriptors of hydraulic properties at a small scale, the scale at which we measure, may not be applicable to the hydraulic properties of those same things on the scale at which we model. And if that's the inference of the question, then I agree 100%. Now, geostatistics does allow us to accumulate, we can have a variogram for averaged properties, but that mathematics is there, but that assumes that that stationarity applies. In general, average properties will have less variability than individual properties. So the answer to your question is, again, terribly unsatisfactory, deserves ordinary attention, but upscale properties will tend to have less variability than just point properties. And if the scale of upscaling is the same as the scale of the variogram, then maybe they're less dependent between each other. But apart from those heuristic rules, I can't say too much more. But then this is totally unsatisfactory, I agree. This is something that needs more attention. I haven't given a straight answer yet, have I? And I'm sorry the answers aren't straighter, but we can still do lots, even with these unsatisfactory answers. But the implication, like the need for a prior, means we're living in a highly parameterized world. Good. We've moved away from the times when we had to simplify and parsimonize parameters. In doing that, we built in bias and we were unable to quantify predictive uncertainty. Now we can, but the ability to do that comes with the responsibilities of defining good priors. And that's responsibilities we haven't quite taken on, because as an industry, we've sort of got one foot in each camp at the moment, I think. Part of us is still living in the old world where we used to parsimonize. Part of us welcomes the ability to live in a highly parameterized world, but that same part hasn't taken on the responsibilities of defining the priors that we need to have to live in that world. Okay, next question. I know you did not discuss this today, but for a multi-layer model, can you still estimate parameters without having pilot points in all layers, especially if the layers are arbitrary, particularly set up for transport? Yes, there are, as we'll talk about in webinar 3. I mean, this is another one of these unsatisfactory things. You don't have to use pilot points. You don't have to use pilot points. When we use ensembles, there is no limit to the number of parameters that we can use. We can use millions. We can use cell-by-cell parameterization. Now, this is a good thing and this is a bad thing. If we can use cell-by-cell parameterization, we haven't got to deal with the artificiality of pilot points. So we've gained something and we've lost something, okay? You're not going to be able to calculate a Jacobian matrix anymore, but doesn't matter. It's done behind the scenes. You can still fit the data well. You can still quantify uncertainty well. But you're not let off the hook when it comes to defining your prior. So you're going to, if you've got 1 million parameters in your model cell and you've got another layer with another million, you've got to come up with a prior probability distribution for that. Now, are you just going to say, well, I'm going to welcome all this complexity, which is good, but now I'm going to dust over all that complexity with a multi-Gaussian prior? Is that good? Well, it works. Is it the right thing to do? Sometimes, often we can get away with it, but it's a totally valid question to ask. If we're going to have that level of parameterization complexity, do we need to get a little bit more sophisticated in our stochastic complexity? The answer is yes. But then we run into other problems. The theory on which ensemble methods are built is kind of Gaussian, and it's an area of active research to move away from there. But that area of active research is still exactly that, active. There's no very nice answer to your question about how we can do realistic descriptors of cell-by-cell stochastic complexity in ways that are not multi-Gaussian, more geological realistic, and still use ensemble methods with full integrity, an area of continuing research. Okay. Hello, Harry Ash. Hydraulic conductivities or log hydraulic conductivities for the multivariate Gaussian distributions. If in doubt, log transform. Log hydraulic conductivities. Yes, log. Okay, any other questions? Well, if there's no other questions, then yes. Can CK, of course it can. CK not only can, So the question, can CK include vertical dependence? It has to. It has to. Like if you build a CK matrix where you're saying that you've got submatrices which don't include the vertical dependence, I mean, you can't wash your fingers of defining statistical connectedness. If there's none, if you say the off-diagonal elements between layers is 0 for convenience, well, you've said there is no statistical dependence between those layers. Now, that may be the case, but if it's not the case, then you need to put in off-diagonal elements which can accommodate statistical independence between the layers. It's got to be a conscious decision and not a decision of convenience. No matter how big your K, notionally there can be a CK that is big enough to embrace it, but it starts to get very hard to handle numerically when we've got giant CK matrices. So in principle, yes. In practice, things will get difficult, but if that vertical dependence has an effect on your predictive probabilities, then yes, you've got to include the vertical statistical interdependence between the layers. Next question, will recordings be available in case you miss a presentation? The answer is yes, the recordings and the slideshows will be available. Okay, well, can I just say before we finish, thank you everybody for, I mean, this is 1 hour and 21 minutes we've been at it now, and this is a long webinar, and it's been a pretty hefty webinar, but thank you for staying in attendance, and I hope that this, well, by dredging up things that you already knew, I hope it hasn't been too painful, bringing back some of the traumas of school back into the front of your brain. Next week, the equations will be a bit longer, but we will be on a journey to someplace pretty interesting. So that's not next week, next webinar, that's 2 weeks. So thanks for attending, and we'll see you in a couple of weeks.